on this computer. Guys, we're going live. All right, here we go. So if I look at, and I put my finger out in front of me, have you ever noticed that when you, hopefully you guys can see my face right now. When you guys ever done this? You kind of bounce your face, your eyes, you open one eye, you close one eye. You ever done this? Like that? You look like an idiot when you do it. But when you do that, have you ever noticed that?
Yeah, it's called parallax, right?
Yeah, perfect. And if you notice that the thing in the background moves. But if you,
which eye is more dominant. Yeah.
Ooh, okay, so yeah, so we have that possible issue. But then also, if you look, does the
Based
mountain
on positioning?
Mm-hmm. And if you notice, that mountain is closer, right? And so as the person looks in their left eye and right eye, you can see a big difference between the mountain. But look at that, I don't even know what that bright light is. Is that the moon? The moon doesn't do as much, okay? So parallax is gonna be interesting. We're gonna get after it, you ready? So here's us. So I think it's first is we gotta talk about this picture. So when we talk about parallax, Alice does this in his math class. We talked about parallax and he's been nerding out on it. It's so cool. So as we go around the sun, okay, if I think about it, it takes us 12 months to go around, okay? 6 months later, I'll be in the completely opposite side. So as long as I have a calendar and I go, I'm gonna take a measurement at one point and I'm gonna take a measurement 6 months later. I can make a measurement and I can look at a close star and I can compare it to the background stars. Here's why. The background stars aren't gonna move during those 6 months. But that nearby star will look like it's in a different spot because of this concept called parallax. I want to show you in the next slide. I found this one. I stole this. Oh, I got to do this one instead because this one actually lets me show GIFs. So here's a, can you guys see my screen? Not on the Join PD, but I found this. I even cited my work, kids, just emphasizing the good stuff. They said, hey, 6 months apart, this is what the skies looked like 6 months apart. Do you see how the background stars are in the exact same position? But the upfront stars dance back and forth. Isn't that weird? And that's because the ones that are dancing back and forth are close to us. And so if we measure that angle difference, because these we can't measure physical distances, we can only say, how does the angle that I have to look at is different? If I look at that angle, and here's the key to this whole game that we play. If we say we are 1 astronomical unit away from the sun, we can now say how far away that star is in terms of astronomical units. In other words, solar distances, us from the sun. And that's all we do is we just compare it to that solar distance. And that's it, okay? And so any questions on parallax? Because this is, if we can't do this one thing, we can do nothing in knowing how far away stuff is. That we literally have to stop everything because we have no way of knowing how far away it is. So parallax is step 1 in an astronomer's toolkit. Okay. Okay. Give me a chance to ask questions, but if I don't hear anything, we're rocking and rolling. So in the middle is hopefully something that makes sense to you. A candle and a ruler, right? That ruler, as you look further away, does the ruler get smaller? So somehow somebody bought a 6-inch ruler, okay? So first up, maybe they're in the middle of a quarantine and that's the only ruler they could buy, okay? So let's not give them a hard time. But as you look off into the distance, see how that ruler gets smaller. Those distances get smaller. And also notice the light, that luminosity in that candle will be the same everywhere, all the way down that line. But it's dimmer the further away it is. So if I knew, this is key, if I knew what the standard candles were, in other words, if I knew, hey, Bert's got a flashlight, Scott's got a flashlight, Alexi's got a flashlight, and we go down to Union and we have you spread out down the football field, I could look at the brightness coming from your flashlights and I could say how far away you were. If I knew that you all had the same flashlight and I knew how bright the flashlight was at a certain distance, I could then calculate how far away you were. Isn't that kind of cool? We call this idea a standard candle. Okay. Does it mean that there's candles out there? No. Okay, please do not think I think there's candles in space, all right? But if we knew what the standard candles were, we'd be rocking and rolling. Wouldn't that be cool? So, hey, throw it out there. Who knows if some of you thought about this stuff? Are there any standard candles that you guys have ever heard of? Let's see what you guys know. What do you guys know? Sometimes people have heard a couple. If you haven't, that's totally cool, by the way. You guys ready? You're going to hear some of these and you're going to be like, oh. We got two types of stars that are actually close to us. Okay. When I say close, they're not close. Okay. They're far away, but they're close enough that we can do parallax measurements with modern telescopes. Tell me if you guys know how to say this, Cepheid or Cephid stars. What it is they change their brightness. I want to just mess with your head. What would it take for a star to change its brightness? What would it take?
It starts dying.
Starts dying? What else? Keep going.
Less energy.
So it's losing energy? What else? Good job.
It's moving further away.
Yeah, so it's moving, right? Good. Keep going. This is really good.
It's behind something else.
So maybe something's moving in front of it. Good. There's one more that we will never talk about because it's far too complex for us right now. We're just trying to hit some basic ideas. Stellar dust. The Milky Way, we have a lot of dust. We have a lot of particles that just get in the way. And so we actually have some spots that are kind of darkened out. And it just screws up measurements. But if we look at different wavelengths, they actually come through those dust better. And so we can kind of go, okay, where's the dust? Okay. If you don't know where the dust storm is, it screws up all your measurements. If you know where the dust storms are, you can go, haha, we're good. Cepheid stars are weird. They actually change their size. I'm tempted to make you look at me right now, but they actually change their size. And over a 9-day period, this one that we're looking at, and so we refer to them as Cepheid stars if they do this over a small, like 2 months or less, okay? These are hot stars, but they're not too hot, okay? They're luminous, but they're not too luminous. 40,000 times luminous than our sun. Only 6,000 Kelvin. Our star is about, I believe, 1,500 Kelvin. What's the temperature of sun? Who knows that one? I don't. We're about 6,000. So similar to our sun. Oh, wow. I thought it was 1,500. That's our oven. Sorry. We're top of a light bulb. Oh, wow. Okay. Notice how they take between 2 and 60 days. Okay. And we can actually look at these things. We know they're not going away from us that fast because of the parallax. So we know that their changing brightness isn't from that. Here's what's cool. You ready for this? Okay. I'm going to make you look at me. I'm so sorry. The schmear is here. You ready? Watch this. Oh, I gotta hide your names just so somebody looking at the recording. Right? Here's a star. Oh, geez, makes me realize my head's a melon. Okay, watch. If your star collapses a little bit, it has more pressure, more heat, and it heats up. If it heats up, what happens to its brightness? It goes up. Okay, ready? But as it heats up, guess what happens? It expands a little bit. It'll produce more helium, and the helium will be on the atmosphere, and it'll actually get a little bit dimmer. And as it gets a little bit dimmer, it cools. So as it expands with these new particles, and it gets a little dimmer, and it starts to cool, it collapses down. Well, when it collapses down, it heats up a little bit. It goes back up, and it just keeps doing this for a long time. So guess what? We look out there and we find these stars that do this, who change brightness over time, and we're like, that's pretty cool. Okay. So here we go. So those are Cephids. And then we get to these little bad boys. These guys change really fast. Okay. You will notice cycles on these. They're called RRs. I think it's Lyrae. I just know them as RRs. Whenever I see the symbol RR, I know these are like super fast. Okay, they're not as luminous as our sun. Sorry, they're more luminous than our sun. They're really bright, but they're not super luminous. Okay, and they oscillate really fast. So imagine something the size or bigger or a lot bigger than our sun that changes its size that quickly. Okay? Holy smokes. These things are just bouncing back and forth. But because of it, we can look out there and we see these things and they're oscillating. Now, guess what? Using parallax, we can know how far away some of them are. And then guess what we do? We know what their brightness is, and we see different ones, and we go, okay, we kind of see a certain period of them, and we can kind of classify them. We classify a lot of these, ready? So now when I look out into deep space, and if I look at a galaxy and I see this thing oscillating, and it's changing its brightness, guess what? I can compare it to a star that's close to us. And I now know how far away that galaxy is. Isn't that cool? Like you can literally go, that's like one that's close to me. I know the brightness of the one close to me. So if that's this certain brightness, I know what the luminosity is of that one that's 40 million light years away or 5 billion light years away. I can look at it and be like, oh, I know how far away that thing is because I can compare it to something close to me. Isn't that cool? Because when I take you on the next one, this is the most controversial one, but this is the one that's easiest to remember. Okay, SN1As, so supernova 1As. These are super cool. Okay, you ready? You've got you got to go with this. You've got two stars oscillating, rotating around each other. One of them, so we're going to talk about how this happens, turns into a red giant and collapses down to a white dwarf, and then they start to devour each other. Okay. Well, during that collapsion, we see this huge supernova. And what we've noticed is we look out, we see remnants of them. I think I'm scared to commit to a number, but it's not that many. We haven't observed many, but we see things that have the telltale signs of being them. They're really bright. They overcome the brightness of everything that's happening around them. And so they're really bright. If we look out there, we see these little dots and we go, those are little supernovas. I think I copied a picture of one of them. This is how it happens, right? They circle, one becomes a red giant, and his atmosphere and his outer shell start getting consumed by the other one. He turns into a white giant, and then supernova action, and it's just exciting. Okay, it is good times. They're really cool to see. They're beautiful. Here's one. Okay, happened in 1994. I referenced it. Guys, you don't have to believe me. You can trust the internet. And when we see these, they're super bright. It doesn't mean they have. It doesn't mean they're bigger than the inside of their galaxies. It doesn't mean. It's literally saying they took an entire star, collapsed it down, and it supernovaed out. So we're going to talk about what a supernova is in a second. But since they're super bright, if I look out and I go, I see a supernova, but it's really dim, that just tells me it's really far out there. Super 1As are pretty much very similar to each other. And so we can draw conclusions from this, okay? What's beautiful, this is why I love science, they're noticing that supernova 1As are actually a little bit different. And so the research is changing. And so our distance measurements with them is not as strong right now. And so we have a little bit more variability with them, which is cool, which is fine, okay? This is 2014. I typed it as 2104 just to have fun. And so now I'm second guessing everything I do in life. And so 2014, there we go. It should say that at some point. There we go. It didn't. But it's 2014, they saw this one and they looked at the before and after, and then all of a sudden it's like, whoop. So imagine you look out in the night sky, you're like, oh, look, there's a galaxy. And then all of a sudden you look back and you're like, oh, look, a really bright spot. Super cool, super cool. They're so bright. Supernovas are so bright, so much energy coming off of them. You could almost see them during the day. You can see them with the naked eye, which is amazing. Picture something millions of light years away, billions of light years away, and all of a sudden you're like, I can see it. That to me is amazing. Okay, they'll outshine their galaxies. Okay, so once we know how far away things are, okay, again, you got to see my face. I'm going to make you see the schmear. Here, you watch. We know how far away they are by comparing them. Brightness can tell us something about the luminosity if I know how far away they are. Colors can tell you about temperature. Okay, so we've got temperature. We look out there. We can start to do sizes. We can do distances. Further away, I can start to draw conclusions about ages. Okay, so this is where we're gonna kick it off. You ready? Okay. HR diagrams. Okay, this is like pay dirt. Okay, so if I were to think of my sun, so okay, you guys call it your sun. I don't have a sun. I have a star. Its name is Sun. Okay, I have a friend named Josh Sun, so that's even funnier to me. And so our sun is on here somewhere. Let's see if I can point at it. It's right here. Come on, where's my annotations? Come on, let Schmear show an arrow. There's our sun. We refer to this as the main sequence. Okay, this is really where we notice that stars live. As stars age and as they go through their life cycle, will follow the main sequence. Okay, so our sun happens at its temperature. Okay, and we refer to it as basically normal. That's our sun. Okay, next step, absolute magnitude. In other words, how bright is it? Luminosity. Guess what we call it? One luminosity. It's the sun we're used to. So we say one luminosity compared to the sun. So really, the temperature of our sun and okay, we call it one luminosity. As we go up on this, we're becoming more luminous. It is outputting more energy per second. So this guy here, Betelgeuse. Let's do Betelgeuse. No, let me click. You guys ever heard of Betelgeuse? He was in the news the other day. How do you spell it? Betelgeuse. Yeah, I did it, people. So this is out in Orion, 617 million kilometers. Seems like a far away, but it's 642 light years. So if you went speed of light, it would take you 642 years to get there. And you look at Orion, and Betelgeuse will be his shoulder. Okay. What's cool is we look in history books, Betelgeuse will oscillate and it'll actually change, which should tell you something, right? It tells you what type of star it is. It actually, as it's growing, we're expecting it to supernova at some point. We don't know when, but when it does, you will actually be able to see it during daytime. Okay, huge amounts of luminosity coming off of this thing. Okay, you kind of get an idea. It's really bright. Okay, now notice its temperature though. It's not that hot. Okay, so as we move to the left, now all of a sudden we have very hot stuff. Okay, so Sirius is very bright. Sorry, let me phrase that. Is very hot. Okay, but its luminosity is not as much. It's not putting out as much energy. Okay, so the main sequence, our star, our sun will follow the main sequence, okay, until it gets really cold, and then it'll eventually peter out and just become, I believe it's going to be a white dwarf eventually, billions of years from now, okay? Now, you're noticing here, we also have some other weird stuff going on here. Unstable things do not fall in the main sequence. They're going to jump and they're going to do their thing, and we have this little area. Remember those RR Lyrae, and we've got the Cepheid stars. They sit in this unstable. They're unique little things. That's why we like looking out there, and we don't accidentally mistake them for just a star going through its life cycle. Instead, they're unique. That's why we use them. Supergiants and giants. Okay, they're big stuff. Okay, this is the actual data. Okay, this is actually what we've seen. We look out there in the night sky, our sun is here, okay? And then we see hotter things that are more luminous, okay? We see dimmer things, and then we see white dwarfs, and then we'll see giants, okay? And then our supergiants. This is it. These are called HR diagrams. If you go into astronomy or astrophysics, this is your life, okay? Because when you look out there, We know that a star we see will fit on this, but you're also smart kids. Do you also notice that we've got just some outliers here, right? There is still a lot of stuff we're learning, which is really cool. I like it. I think it's good to share that. This is why it's important that you guys have this in your hands, because this here is the life cycle of stars. Okay. Let's see. Can I make this bigger? I don't know if I can make it bigger. Full screen. Okay. Here we go. So on here. Okay. Okay. How are we doing? Do we need a little break? Do we need to just like talk? How you guys doing? Give me something.
I think I'm good.
Okay, cool. Okay, we got one. It's not bad. I mean, there's like 12 of us, but you guys okay?
Good.
Okay, cool. We got a couple good. We're good.
Yeah, we're good.
Okay, speak up with questions, okay? You guys' questions are much better than me talking. So let's talk this through. So we're going to talk about low mass stars and high mass stars, okay? Low mass, that's us, okay? So let's start there because that's kind of what I want you to think about. So this is the timeline right here of a low mass star. It burns slowly, okay? So here's our sun. It's the easiest way. Think of our sun, right? Right now what's happening is it's fusing together hydrogen, which then becomes helium, okay? But then it starts to, once all the hydrogen gets fused, well, then what does it have to do? Then it has to fuse helium. But, oh man, you guys deserve the best. Decay, fusion, binding, energy, graph. Can't believe I didn't put this graph on here. I feel bad. I feel bad. I have failed you. I'm so sorry. Ooh, I like this one. There you go. That's actually a pretty good one. There you go, buddy. Okay, so if you've been in chemistry, you've looked at this. Iron is like, there's a reason why we have lots of iron. Okay, ready? Hydrogen, it doesn't take much to bind it. Okay. Helium, it takes more to bind it. Okay. Full-blown helium, in other words, full-shelled, full nucleus helium takes more to bind it. Oxygen takes more, iron takes the most. Okay, so imagine this, you're a star. What does it take? Oh, that one's even better. What does it take to fuse these things? Gravity. The gravity slams these things together, creates all of this heat, which then, and pressure, which then allow you to fuse them together. Once you fuse them together, you now have a release of energy. Well, that release of energy then continues the fusion for other atoms. But it takes more energy. I'm going to lose my voice in a couple minutes, guys, so bear with me. It's going to take more energy to fuse helium. So guess what happens to your star? Once you fuse, what happens is to fuse helium, it has to collapse a little bit to have more pressure. And then when you burn through all the helium and you fuse it together and make carbon, it takes even more to fuse carbon to make oxygen. It's taking more and more and more every time to fuse together to make these heavier atoms. And then it eventually gets to iron and it's done. It's dead. But guys, remember, this is a giant, massive thing. If all of a sudden you've burned through all of its energy and it's collapsed, right? So picture, you've got something that's really hot that pushes outwards. I gotta find a good way to say this. Just give me a picture so I can talk. There we go. Okay. So as you have gravity pushing in, what keeps the star from collapsing? It's energy pushing outwards, thermal energy. And where does that thermal energy come from? It comes from radiation. Well, what happens when it stops fusing atoms? When it stops fusing atoms, it collapses even more. Well, here's the problem. When it collapses more, what's going to keep it from just going inwards? Nothing. It keeps collapsing inwards And it eventually hits this beautiful spot when it collapses inwards that it just goes, I'm good. But when that happens, these giant shock waves come out in the atmosphere of the star, the outer shells of the star that are just hydrogen and helium, just leave. They don't have enough gravity to hold them inwards. So guess what? I'm out. Then you're left with a white dwarf that's really hot that will eventually become dark enough over cooling down to become a black dwarf. And so it eventually dies out. Okay, so this is our star. Here we are. We're doing our thing, right? And what's going to happen eventually, it's going to become a red giant because it's going to swell. And then eventually it's going to cool down enough and collapse on itself. And then it's a white dwarf. And so as we look out into our universe, we'll see little white dwarfs. There's a reason why we don't see black dwarfs very much, because they're really dark. They're hard to see, okay? There are some times where we see them. We'll see two stars orbiting each other, and we're like, what's the other thing? And sometimes it'll be a black dwarf, and we'll see some reason to think it's a black dwarf. Now, that's if you have a small mass, okay? We're talking 1 solar mass, which is our sun, or something a little bit bigger, like to 1.5. But what happens if you have something that's super massive, okay? We're talking above like 10 solar masses, okay? This is where it gets interesting. You ready? You guys ready? This is where it gets real. That means you have a very massive star, which means you have huge amounts of gravity, which guess what huge amounts of gravity means? You can fuse your hydrogen faster. Guys, if you can fuse your hydrogen faster, guess what happens? You burn through your fuel faster. If you burn through your fuel faster, you are brighter. Okay? Well, guess what? If you're burning through your fuel faster, what's going to happen to you? You're going to burn out faster. Maybe this is just a life lesson, right? Don't burn out. Okay? So literally, these things burn out faster. I think what's interesting, now you take it a step further and you start to think history, right? You start to look out there and you start to look for these different stars. Okay? If these burn out faster, wow, I mean, it then opens your eyes to be like, well, where am I going to see them? What types of galaxies will I see them in? Will I see them in old galaxies or new galaxies? It's just really cool. I mean, you can start to dig through it that way. Well, what happens to these things when they burn through the fuel? Exactly the same thing that happens to us. They become giants, but they're huge. There's huge amounts of mass. So we're talking 100 to 150 solar masses. These are just massive, right? So what's going to happen? Well, when they collapse, Betelgeuse falls into this. When they collapse, this is when you get your supernova, okay? And since you have so much mass, we're going to talk about, you have one of two things. You either get a neutron star, which are, neutron stars are cool. We're going to talk about what that is, okay? Neutron stars, or you're going to get a black hole in the center. Do you have the gases leaving? Yeah. So here's a beautiful thing. If we think about, oh, this is going to be good, this is going to be good, this is going to be good, okay? As I think about this, a normal star just going through its life cycle won't give us atoms heavier than iron. They can't, okay? So this is where you got to stop and think, where does uranium come from? Where does plutonium come from? Where does wolfram? As you look at this thing, where do all of these different atoms come from? Xenon, arsenic, copper, gold. Where do all of that stuff come from? They come from these supernovas. Because during the supernova, with all that gravity, as you take all of those atoms and collapse them down, you can form these heavy atoms. So then what rebounds out of the supernovas? The stuff of solar systems. How are you going to build a rocky planet that has something with a heavier atom than iron? It takes a supernova. Okay, another model that's coming out that they've talked about also is at the Big Bang, you know, we had trying to think of different mechanisms after we had star formation and galaxy formation, also thinking, could we have gotten some at that point too? Which is an interesting thing that I haven't read much up on, but I do know out of supernovas, we're getting those. If you look at the gases, it's really cool. You could actually do this. Chandra, spectra lines, heavy atoms, because heavy atoms, if you go here, you can actually go and check out what the Chandra X-ray Observatory is seeing, and you can actually see, you can look and see where different atoms are forming on these supernovas. It's really cool. You can look at a picture of it, and you can look at the inside and the outside, and you can actually see it. I'm bummed I don't have a picture of it. I feel bad. I'm so sorry. But here's what you can do. You can actually take a picture of a supernova, and you can look in the middle, and you'll see some spectra of line, and you look on the outside, and you'll actually see heavier atoms. You'll see more silica. You'll see more oxygen. You'll see these different things on the outside, where if you look on the inside, you'll see different atoms. It's super cool. It's a really cool thing. I know Cy Ollie had a competition with this, and every now and then we have students who do it, but super cool. I met the lady who runs it. She's like, yeah, you can like look on the outsides and the insides and see different atoms. I'm like, okay, that's cool. I'm like, I'm all in, right? So yeah, hopefully you guys are excited as I am. Black holes and neutron stars. So I'm going to give you a piece of information, and then we're going to talk about what a black hole is. That's the goal of this. We've built up to this moment. A black hole is just a big star that's collapsed. That's it, okay? So a neutron star is kind of special. It's not big enough to be a black hole, but here's the difference between a neutron and a proton. A proton repels. If I put two protons together, they repel each other. But if I put two neutrons together, they're totally cool being right next to each other. They're totally fine with that. So a neutron star, I'll give you an idea of a neutron star. If I were to take our sun and collapse it down to a neutron star, it'd be the same size as Manhattan. Okay? So picture our entire sun, the entire mass of our sun. And if I were to collapse it down to a neutron star, it'd be the same size as downtown New York. Right? That's it. Same exact mass. If we were next to it, we would orbit it exactly the same. That's what's nuts about a neutron star. They're really hot, so they still emit light. They're really cool. They're super small, so they're hard to see. And guess what? They're getting pulled in with gravity. They're bound together. They're just a glorified giant atom, okay? Because what is it that makes an atom? It's the number of protons and neutrons. Well, they're just a giant nucleus, but they're between 1.4 and 3 solar masses. So 3 times our sun down to 1.4 times our sun would be a neutron star. Kind of cool? Black holes, the threshold is 3. If you get to 3 times bigger than our sun, you now got enough mass to make a black hole, which leads into the next question. What the heck is a black hole? Okay, that was the goal of this whole thing, right? What are some different ways we know we have neutron stars? Because we have this thing called pulsars. We actually have these X-ray emissions coming off of their poles. It's these super cool magnetic fields that come off of them. And so as you look out there, we see these weird rays of X-rays bursting at us. And we're like, what is that? And we look at it and we realize the only explanation is a neutron star, okay? Black holes also emit X-rays because as the gas come in, they'll emit X-rays off of their rotational points, okay? So we have some different ways of kind of going, what's out there, okay? But this is it. You are looking at the life cycle of stars. When we find something that doesn't fit this, we get really excited, okay? If we get enough data and we look at it, we go, it doesn't fit this, we either have to change our model or it's something else, okay? There's one more out there. It's called a brown dwarf. They're really hard to see, guys, because they're brown. They don't light much. There's not much, they're not very excited. These things last really long, okay? Our star isn't going to last that long. It's going to last, you know, I was at 4 billion years. Okay. And then you talk about a brown dwarf, they last a long time because they don't burn through the fuel fast. They're at a very steady state. Massive stars, they burn through really fast. Okay. I have that there because to me, this is it. It is to look at this life cycle and go, all right, what's going on? Okay. Before we go into black holes, I've been waiting for this all day. Black holes. Before we do it, any questions on this? Ask away. We'll see if I know the answers.
I just had a quick question about like the coloring.
Yes.
Are the coloring of all the stars in this cycle like accurate, or is it more of just like a aesthetic kind of thing?
Oh, Asia, that is a good question. Okay. So, okay, to give you an example, right? When I see, let me do this. Okay. So there's lots of things we need to answer right now. Okay. This is the picture. It's called the Hubble Deep Field. Okay. This thing right here.
Yeah.
Okay. The question is, from Earth, are they actually those colors? That's the first question. Let's start there. No.
Yeah.
Okay. 2 reasons to answer it that way. 1, they're too dim to see them with the naked eye. Okay, that's the first reason. 2, the stuff that's really far away is moving away from us so fast that it's red shifted completely into the infrared range. So with the visible eye, I could see none of this. It's all red shifted so far into the infrared, I can't see it. And this is why it is so important that we get this thing launched as soon as possible. This is called the James Webb telescope. We're going to put it into orbit. It's going to sit there, and it can only see infrared. And it is going to, we're going to learn so much because it's going to give us the best picture of infrared. Okay. Infrared from Earth is really tough because infrared is absorbed by water molecules. And our atmosphere has a lot of water in it. And so infrared, we have a hard time seeing it from Earth. Hubble does pretty good, but we don't have much out there in space to see, right? And so the James Webb, we got to get this thing off the ground. It is one of the more beautiful modern things we've ever done. Okay. So now, Asia, I feel like you tipped off on a question. So then how do we decide the coloring? Well, one thing we do is we go, okay, what's the temperature? Okay. And then we'll match it to what the temperature would be if we looked at it on Earth. Okay. But some of the things are so cold that they're still in the infrared. So you literally have artists who, that's the thing, I can't call them an artist. They're still a scientist and a physicist. They choose what color of visible light goes towards certain wavelengths of light. And what they do is they choose, okay, this low range is this color, this high range is this color, and then everything fills in.
Okay,
And
so it's more like relative.
it totally is. And that's what is tricky and frustrating. But here's the thing, this Hubble Deep Field, if I compare all of the orange stuff, those are consistent. If I can charge all the blue stuff, they are consistent. But almost all of this stuff is shifted to infrared and visible, non-visible light. Isn't that weird?
Yeah.
Yeah.
That's really weird.
And what's funny is I was talking to the lady, she works with Chandra, the X-ray observatory. They're just observing X-rays, right? You can't see an X-ray, but they take that data, and there's literally a paid person whose job is to take those things. Because when you see, you're like, what's a famous one? Orion Nebula, I think is one, right? It doesn't look like this. But there's somebody who goes, all right, I'm going to take this real data, and what I'm going to do is I'm going to choose what the visible light is here and here. You're literally seeing infrared light here, but they put it into visible to show you, but then they're consistent throughout the picture. That is absolutely vital, is they are consistent in the picture. There's some that cheat. Now here's the thing, you ready? They don't even tell people who their artists are because they'll offer them more money and they'll lose them. So it's actually this really cool thing that they do. They like hide each other's artists. And I heard that, I'm like, sick. This is rad. Oh, thank you. My wife is so patient with me right now. Every now and then I'll send her an email. I'm like, could you print this? And like all of a sudden a piece of paper shows up. No, you are amazing. Okay, so she's an online teacher with her kids in preschool. She's homeschooling my girls. Did you go to Chuck's? Yes, she went to Chuck's. We got food. And then me, I just sit at the computer and talk about black holes. Okay, so neutron stars. There we go. I showed a picture. There it is. Earth, white dwarf. So picture taking our sun and it collapses down to a white dwarf, right? It's about the size of Earth, right? And then you see a neutron star. That speck is far too big, but I still put it there because if I just pointed at nothing, you'd think I was pointing at the white dwarf, okay? Do you kind of have an idea of size? Is it getting crazy? Okay. Oh, ladies and gentlemen, I want to welcome you to 1912? 15. Guys, yeah, 1915. 1915. Okay, Einstein shows up. He had a really super cool, so in 1905, he did special relativity and talked about the energy of light. Huge breakthroughs, okay? Then from that comes Niels Bohr. From that comes Rutherford. I mean, Madame Curie comes from those moments. I mean, super cool stuff. It all flows out of these discoveries. No, Madame Curie was before. She did radon. That was different, separate idea. But the quantization of light led to quantum mechanics, thinking about these really cool things. Things just flurried from that. And then he finally came across, and here was his issue. You guys ready for his issue? Because Maxwell, electromagnetic lights. So come on, show it to me. There's got to be a good GIF. Sorry, GIF, forgive me. For I have, no, I don't want Khan Academy. Okay, let's do, there she is. Here we go. Come on now. No. Why are you showing me that? This, okay? So Maxwell, he did a whole bunch of math. Yeah, I got to start with this. Math literally progressed because of physics in this like 10-year period, okay? Kepler and Newton invented calculus. Einstein just applied these mathematical ideas. Maxwell was looking at electricity and magnetism. And Maxwell combined electricity and magnetism. And he realized that the interaction between magnetic and electric fields happens at this speed limit, that there's a limit to this interaction. And he found out what it was. And it was, I know it as 3 times 10 to the 8th meters per second, which is huge, super fast, okay? And he did that. Einstein then comes along in 1905 and he goes, well, he starts to talk about as you move, how light acts different. And the only way to describe that is how lengths change. And so he starts talking about how as you go faster and faster and faster, your lengths change, your time changes. And he was really frustrated with that. And over the next 10 years, he develops his next theory, and it's general relativity. And the way that he was able to reconcile the speed of light being constant, because Maxwell's equation said this thing that's electrical and magnetic has to interact at the speed of light. Einstein goes, that thing is light. And then from that, he goes, if it has to be going the same speed, the only explanation, oh, easy now, is that space and time are affected by mass. And it's like, whoa, what did you just say? And he basically said mass warps the actual fabric of space, okay? And then if he just said that, it'd be no big deal. But then he applied mathematics to it to talk about orbits and to talk about the motion of Mars and Venus and the Earth and how we move about the sun and trying to come up with these explanations. And the only way to do it is to use his mathematics of general relativity. So I'm going to give you a couple situations that he come up with. First is a sweet video. I have to go back to this one, and I'm down here. Found a couple of videos. If we were in person, we would do this. We did this with STEM for our field day with the little grade schoolers and middle schoolers. So let me show it to you. So we've got a black thing. It's like a tarp. Nice job. He's got a cat. I just stole this guy's thing from online. It was really nice. Okay. See how it warps space around it. The mass warps the space. And you see how the ball is affected. And see how it goes in a circle? So instead of coming up with these weird ideas that Newton came up with, like, oh, we have this force and it magically happens at a distance, Einstein goes, no. Instead, mass warps space and we're just falling towards it. And that's it, right? So that's it. That's it. That's all he says, right? And then he's like, okay, let me show you another one. Here we go. This one's a little better. This is one of my favorite things. We'll do this in class. I mean, I wish I was face-to-face. He's got a ball filled with lead. Should be. There it is. And he's just got a trampoline. And, right? See how smaller stuff warps things less. Okay? So, here we go. Here we go. Come on, buddy. Come on. Show me the last one. So here's what he hypothesized. Because if Einstein says all this stuff and it doesn't, and you're sitting there, you're like, whatever. So Einstein goes, hey, if you have an eclipse and there's a star behind the sun's going to be able to warp it enough that you're going to be able to see it. So do you kind of get the idea? Remember, Einstein, so some of you, this is what I love about class, and I think you guys have seen this in class, that some students in class are all about just the ideas, and they keep it up in their head, and they reason it in their head, and they're not too concerned, they're not even concerned about the lab. These are theorists. And I have a good friend, his name's Stamatis Vokos, and he's an SPU professor and in the physics department. He's a total theorist, okay? And it is fascinating to watch him work, because he can do it all upstairs, and he just thinks about it. That's what Einstein did. He just thought about it. And he goes, now you go and find a situation. The experimentalists, I got a lot of friends who are experimentalists, and you see the people in class like this. They love to get their hands on it. They want to show it through experiments, okay? That'd be like a biologist who wants to talk about it and a biologist who wants to like be doing DNA stuff in the lab and showing it, having it come to life, right? And so Einstein's a theorist. And so he says, hey, this is going to happen. Our sun has enough mass that it'll warp space this much, and you'll be able to see a star that's behind the sun. Okay? 1919. His math at the first opportunity to do it was wrong. He assumed something not enough. And so they actually missed the chance to go do the expedition to see it during one of the solar eclipses. It was during wartime. And then after World War I, they were able to go. And by that time, he had fixed his mathematics. And so he was shown that the star would be at a different spot. Okay, this is huge. If it had happened the first time, they wouldn't have seen the effect as much. And they would have thought it was a different idea. But instead, because of the war, they had to wait to do it. And then they went and did it. And here's what they literally did. They did these expeditions. Eddington's expedition did it. And they went out there and they actually went out, took this piece of film. During the eclipse, they had a telescope. They took a picture of the stars around the sun. And this is actually one of them. And it's faint between these. I don't actually know what the little bars are, so please don't ask. No clue. And they saw these stars. But those stars shouldn't have been there. And it was because the sun warped space and bent the light around. Isn't that crazy? Like, picture like right now, the computer's right in front of you, right? And you can't see stuff behind the computer. But if your computer was heavy enough, the light would bend around your computer and you would be able to see it. And that's what Einstein's general theory was, is the idea that space is warped, okay? From this comes another thing, that time is warped. So the movie Interstellar, Who's seen Interstellar? Chime in. Anybody seen Interstellar? You all sleep.
No, but I heard about the ending, which was really sad because I actually wanted to watch the movie.
Oh, go watch it. Oh, don't worry. There's 2 versions of the movie. Don't worry. The ending's not what you think. And so, you're welcome. So we're going to take this a step further. Okay. So now here's Earth, right? And you have a galaxy and you have another galaxy. Okay. You ready? So we call this lensing, gravitational lensing. This is a physical picture of gravitational lensing. You see that big bad star or galaxy in the middle? Huge, heavy galaxy. Straight behind it is another galaxy. And guess what? See that ring? That ring is the galaxy that's behind that galaxy. And guess what? Every now and then, you guys, over the next couple of years, you're going to watch the news and you're going to hear, oh, this is actually how old the universe is, okay? Because through gravitational lensing, we can see further. Get ready for this. Why? Get ready for why? Because there's faint light coming off of a distant galaxy. But through gravitational lensing, it gets bent back and I get more light off of it. And so we can see these very, very faint galaxies. They're in the far stretches of the universe. And we're able to see deeper into the known universe. Since space is physically expanding, to see out there, we have to be able to see very, very faint objects. And gravitational lensing is one of the ways that we're seeing further. The other is sending something out there that can see infrared light and we can look out even further. James Webb, over the next decade, we're going to see the coolest things, okay? It's going to be pretty cool.
Shmear?
Talk to me, Goose.
So how does, you said the universe is expanding, how does that compare to the relative theory, which suggests that everything is falling towards each other?
Oh, good. So as I go out into space and it's just flat, right? So imagine a 2-dimensional, it's just flat. There's no mass impacting it. You don't fall there. There you just sit like nothing's going on. But as you get close to massive objects, it warps space.
Yeah, that makes, okay.
Is that better?
Yeah, that makes sense, yeah.
Okay, this is where it gets good. You ready? Oh, okay. Maybe this okay. I thought of a better way to do it. Okay, I thought of a better way. Hold on. I got it. Okay. For us to leave Earth and go to the moon, do I need a certain amount of speed to escape Earth's gravitational pull?
Yeah.
Do I need a certain amount of energy to get out of the influence of Earth and to get to a spot where I'm free and I won't fall back?
Yeah, you're breaking like the threshold of.
Good. And this is where Einstein, he got mad at us physicists. He goes, no. He goes, because Newton says you throw something up, it comes down. Einstein goes, that's dumb. Because Einstein says, no, if you throw something up fast enough, it doesn't come down. And I'm like, oh, here we go. And so his idea, his concept is if I throw something up, if I throw it fast enough, it leaves. Okay? But you guys ready for this? Is there a speed limit in the universe? You can't go faster than the speed of light. So what if your escape velocity you need, you can never get to that speed? You'll never leave. You can't leave. Our sun, right? Our sun's not that massive. We were able to leave it, right? Right? If I were to shoot off a satellite like the Voyagers, they were able to leave our solar system, okay? If our sun was bigger and heavier, right, would it take more speed to leave our solar system, right? If our Earth was heavier, would I need more speed to leave it? Well, what if I needed, right? Oh, I forgot my pen. Oh, no, right? We're not going to write this today because we're almost done on time. I want you to imagine if there's a point at which you would need more speed than you can physically travel in our universe. You can't go faster than light. How would that work? If you've shown a flashlight that the light is going the speed of light, it's not even fast enough to leave. This is what came from his general relativity equations. Karl Schwarzwald, also Chandra, oh, how do I say his last name? Chandra, I'm not even going to try to mess it up. But Karl Schwarzwald did some basic math, and he says there's a certain mass and a certain size that if you're within that, you can't leave. Okay, and that's not good. Okay, and so we call it the Schwarzwald radius. And so I want you to get thinking about this. In the middle of this is a point in which you can't escape it. You can't leave it. Because it's so massive. It has warped space so much that you can't leave, okay? And so really what it is a supermassive star that's collapsed. And instead of launching outwards, the particles that are making up its mass can't leave. And so guess what they do? They fall inwards. And they continue to fall inwards. And we theorize that in the middle of it, that it's a single point. That all of that mass is at one single point. I have no idea who's let in. Hopefully they're a friend. I should probably check names before I just let people in. Shub Schmear. Yeah, everybody know. Cool. Let's not get Zoom bombed. And so we call it a singularity. It's a spot where really, and Einstein doesn't like it. Okay, he doesn't like it because the mathematics, all of a sudden math breaks down at a singularity. And Einstein doesn't like that because everything he does is based off of the idea that math can explain anything in our universe. Right? That's his idea. That's his concept. That's his modus operandi. Like that, and it has worked. Okay, to understand space-time and understand these really cool ways of talking about space, and we call it field theory. We don't talk much about fields, but we really have an understanding that our universe is made up of these different fields. And really, as we talk about mass and we talk about electric fields moving through space, a black hole screws everything up, okay? Because the mass is in one single point. It doesn't take up space anymore. And to talk about it in terms of mass doesn't make sense. Talking about in terms of energy, it makes more sense. It's literally a whole bunch of stuff in one point, and nothing can ever escape because it has warped space so much. Now, guess what these things do? They continue to consume things. Okay, but let's say our star, our sun, turned into a black hole right now. Right, 8 minutes and 20 seconds from now, it gets really dark. Okay, guess what we would do? We would continue to orbit it like nothing happened, because the mass is still there. We don't fall in because we are moving really fast. The Earth is going really, really fast around the sun. And so we don't fall, okay? But if we lose speed, we start to fall. And so if you look at the gas in the middle, right? Remember, we might have had a supernova happen, a giant supernova happened, and this gas, some of it's going one way, some's going the other, and guess what it does? It rubs up against each other, a little bit of friction. And it slows down. And when it slows down, it gets consumed, which makes it fall into the black hole, and it gets consumed. And as it gets close, it gets excited and emits X-rays. And that's what these beams coming out. So we'll see these X-ray beams. This is how we are able to spot different black holes and different neutron stars, is we'll look for that X-ray beam coming out. But then we also see this disk rolling around. I want to show you a picture, and this is the last thing for today. And we'll pick up where we left off, okay, next week. But this here is our first picture of a black hole. That light you see is the accretion disk that's rotating around it. And that accretion disk, you're actually seeing the light from behind it, as in addition to the light in front of it. So you see these weird shapes. This is from the movie Interstellar, but the person on Interstellar was Kip Thorne. He's a huge, well-known physicist, and Kip Thorne, this is his idea of what a black hole would look like. Veritasium video, go check it out sometime. But he talks about how and why. it's warping space so much that the light behind the black hole comes to the front. The disk is all around it, right? But it's warping that light towards us. And so we see that light. And when we took our first picture of a black hole, this actually, mathematically, it actually matches what we would want to see out of a black hole. Okay. Let me ask you this. Next time we have one of these things, what do you want to talk about black holes? What are you curious about more? Throw out some ideas. What are you guys thinking? It's Friday. I got to go to Papa Murphy's and get some pizza.
Like interactions with black holes, how things around it, how it's going to.
Okay.
Yeah, I don't know.
Okay. So here's our day 3. We're not going to spend much longer on this because I want to talk about time in Switzerland. What happens around black holes? I'm on it. Okay.
If
Anything
energy
else?
is conserved, where does the energy go from the black hole, or that goes into the black hole?
Okay. Okay. Anything else?
I have a feeling that one's going to mess with my head.
You don't know you want to ask this, but that one will come up. We'll talk about that. Entropy, don't think about it. What else? Okay, cool. Anything else? Asia, I think you said something and I cut you off.
Oh yeah. I was gonna say, what the inside of a black hole looks like.
Oh. Can we just start with that one? It's gonna be a lot of energy, a lot of X-rays, a lot of ultraviolet light. But remember, the gravity is so strong that stuff just continues to fall inwards. But here's the catch. As it falls inwards, there's still interactions happening. And believe it or not, this idea of what happens to a black hole out over time, there's some really strong theories. Stephen Hawking has a theory that we are going with, is that black holes evaporate, that somehow they emit X-rays. And it's because on the inside, when things spontaneously decay, we'll have this conversation after we talk about CERN and subatomic particles, but you literally have energy leaving the black hole, and it'll slowly evaporate. And as it evaporates, it gets smaller and smaller and smaller. And so you can actually lose mass by emitting X-rays. What does the inside look like? It's not dark because there's light in there. The semblance, but that's the thing. Now you have so much warping of space and you have so much energy, right? I mean, just imagine what it'd be like to have so much gravity, so much energy crushing you, right?
Yeah.
Would we even be
Sorry.
able to think, because space is warped so much? So now all of a sudden the synapses in our brain, there's like, what happens to the spacing and what happens to the interactions? Like, do the laws of physics still hold true at that singularity? These are literal questions that people don't have an answer to. Time runs completely different.
Yeah.
How long does it take to go from that? We call it the event horizon. We didn't talk about that. The event horizon down to the inside. Like, how much time does it take? I think it's like 5 hours to go from the outside inwards. But you're not in a good spot. And as you get close, you're like, hey, things are okay. And then you get inside, you're like, things aren't okay. They'll never know that you said things aren't okay because it never leaves. But let's say you followed them anyways, right? You would slowly get their signal over time as you fall inwards. And then the gravity at your feet and your head will be different. And so you'll stretch out. I mean, it's just horrible stuff that happens on the inside. It is the coolest physics, but mathematics breaks down. It just gets confusing. And so this is where brings into our last idea, wormholes. one of the theories is that as you get into the base of that black hole, could you then go, since it warps space so much, could it connect to another spot in our universe? Mathematically, we think you can, but once you're in that, inside that event horizon, you can't leave. You're in, okay? But you can see outwards. And so maybe you can go through these wormholes and continually see different spots of the universe through wormholes. And one of the new theories is to understand what's happening in these weird situations. One theory is maybe we have very small wormholes happening all the time, and we just don't realize it. Here's why. If I have, oh, you got to go with this. Electron, positron pair. Okay. If I have an electron positron pair, okay, and we see this all the time, when they are separated from each other, they're separated. But they have certain properties that will maintain even though they're really far apart. But here's the thing, those properties aren't set until we observe them. So if I go over to the electron and look at it and I see it have a certain behavior, I could then go to the positron and I would know what it would be doing even though I never looked at the positron. And it's called action at a distance. And we don't like it. We don't like it at all. And the only theory that they have for it is this idea of possible micro-tunneling of wormholes. And it's still a non-fully accepted theory, but they're trying to figure it out because action at a distance, we do not like, okay? It doesn't make sense. How would something on one side of the universe know what another side of the universe is doing? That doesn't make sense. But somehow they're able to still be somehow paired together. That because quantum mechanics says if I look at it, it'll now have a set state. And that other one will now have the exact same set state. How does it know to have that set state? It's just like, it's mind-blowing. That's where physics is right now. Okay. What's cool is we've now gotten used to modern physics. This is actually stuff that we're actually curious about right now. Okay. Everything we've done this year in class, totally known since 1800s. Okay. Today, in this last lecture we have, is literally early 1900s. Wormholes, quantum mechanics. This is the stuff we're trying to figure out right now. Gravitational waves, we've known about it since Einstein. We finally saw it 7 years ago. So, this is the stuff right now. Okay. Yeah.
Shamir, I have another question. This probably falls under some of the points already listed, but like spaghettification,
Yep.
That's like what?
That's real.
Okay.
Don't experience it.
Yeah.
No, I'm serious. It's really bad. But it's acceptable now. It's really bad. And so what it is the forces become so big that you can't hold yourself together. Okay. Picture playing like tug of war and all of a sudden the rope breaks. Okay. Now imagine playing tug of war in a black hole and you have this rope there, right? And one end of the rope is closer to the singularity, to the center of the black hole. And it feels a greater force. The outside feels a smaller force, and they accelerate differently. And so the inside gets stretched. And so that's spaghettification, where that happens. There's another thing that happens. Is it worth talking about? If you think about our globe, it's a sphere, and so it's a way to kind of model things, right? As these parallel lines, like if you look at these parallel lines, they feel parallel, but as you get closer to this point, my parallel lines start to merge. And that's frustrating, right? And in a black hole, these parallel lines of space-time merge at a single point. And that's why, and this is literally why Einstein doesn't like the idea. Okay, he's like, I don't like it. It breaks it down. It's called a singularity. It's this idea that it all comes to a spot. And so that spaghettification happens as you get those parallel points closer together, because your field changes, your accelerations change. Not on Earth, but in terms of space-time getting warped as these parallel lines go together. This is good. We'll talk about this stuff. It'll be good. So my plan next time is we'll talk for a little bit about it. And then what we'll do is we will talk about, and then we'll start talking about CERN, because the CERN one is cool. I think everybody should learn about it and what they're doing at CERN and LHC, because the US, we're partnering with them for a few more years. Hopefully we re-up it. We'll see who everybody votes into Congress and if they support it or not. So it's always the catch every year. So so it'll be fun to talk about, and we'll talk. And it's cool is we'll talk about more than just physics. So that'll be good. But we'll start by talking about a little bit of black holes, and then we'll get after it. Okay. Okay. I'm gonna take that as a yes. I'm gonna stop.